session. And mostly in this lecture, I'll be talking about object detection, how objects are detected through vision-based intelligent schemes. So if we talk about human-robot collaboration, let's think about the cases. Yes, please.
No, I just started the YouTube, so there was just repeat.
And you have already started recording, perhaps.
Yeah, I just started.
So the basic motivation behind developing these vision-based human-robot collaboration, if we look at this young girl, you know that she is having a lot of assistance as shown here. So every year, millions of people suffer from severe injuries. And these severe injuries make them little disabled, from small disability to very severe kind of disability. And they require long-term assistance and medical rehabilitation. So when we were talking about organizing a course on using a GIAN platform, we thought of different topics, and this human-centered robotics, in fact, to be more precise, rehabilitation robotics was there in our minds. And so we approached Domenico Preciso, who is a well-known name in this field. And so you can see that rehabilitation is an important field in robotics. And medical rehabilitation, if we talk about it, is not only physical, it's also psychological aspects that are important in human robotics, in medical robotics and medical rehabilitation. So looking at all aspects of the patient, starting from his cognitive sensing and physical and psychological problems, a lot of issues arise, and accordingly, robots have to be developed. When we think of rehabilitation or human assistive robotics, there are enormous challenges. Why? Because we have, the process itself is very complex. Then patient's adaptability, even if you make something very good, like think of only specs. Specs is such a simple thing, but if the person is not able to adapt, say the progressive lens, it will be so difficult. In spite of you have the best in the category, you have best frame, best lenses, but it all depends on the human adaptability. And there can be various environmental constraints as well. So take this example where we are expecting robot to like pick something and place somewhere else. Well, the problem is very easy. Pick, that means identify an object and place it somewhere else. There are so many constraints with this. The object has to be lightly handled. The object should not be so lightly handled that it slips away. Depends on the body of the object, everything handling, you know, that you handle your friend with a different hand and handle a bottle with a different hand. How to bring that kind of sensing in the robots, that handling should be accordingly adaptive itself, right? Now, so human-robot collaboration deals with the design and development of, and also the evaluation of robotic systems, which are used by humans, or they work in collaboration with humans. So there is a lot of collaboration that happens between humans and robots, but then this collaboration can be indirect, can be direct collaboration. In every case, we have to take care of what kind of collaboration, what kind of interaction will take place. So these robots interact with humans through various forms of communication. It can be voice, it can be something you are able to see, or some input given mechanically in whatever form, or through various types of sensors that Professor Gupta talked about. So there are various types of communication that take place between humans and robots. So human-robot interaction deals with physical, cognitive, and social interaction. Professor Gupta has already told you various applications, and these all applications of robotics, it require human-robot interaction. One very important development that took place initially was with programmable robots. They were absolutely programmable, no intervention was required. The humans would leave them as they are after doing the programming, putting on the programs. So manufacturing was the first industry where robots were used for mechanization or for automation of processes. Then came the concept of assistance in various other fields, including social robotics with domestic assistance, then surgery, very complicated procedures like surgery, security and defense of nations and specific areas, and then for physical and cognitive rehabilitation as well, gaming. Think of any application, you will find that robots can be used there, right? So human-robot collaboration deals with design and development of intelligent robots nowadays. Intelligence is very important. So intelligent robots that perform actions in the real world scenario with almost, we expect no errors. We don't expect any errors. So that the task should be robustly performed. As I told you, handling some object with respect to what kind of force should be applied so that the object is not crushed, the object is properly handled, it does not slide, it does not slip away. So starting from simply a pick and place type of problem to a very complicated problems like surgery, we expect the robots to be so intelligent that they do not have any errors. They can perform like humans, but humans make errors. But you know that in many very critical applications, errors are not expected, and so a lot of redundancies are applied so that errors could be handled. So they can perform various tasks by successfully completing very complex sequence of actions. And the collaborations should be so designed that they can effectively coordinate and cooperate with people, machines, and there can be other systems as well. And when we talk about this human-robot collaboration, my dear friends, one important aspect is social cognition. And you have very complex social environments like hospitals. Think of hospitals where you have social environment is altogether different than those in schools and at homes. And especially with elderly people, the cognition, the cognitive aspects will be absolutely different than those with children or those in the hospital or at homes. So you can see that there are a variety of different areas and applications where we expect robot to perform as intelligently and as compassionately as a human does. So if we talk about the collaboration levels, you see that there is one concept we can say coexistence, where in the manufacturing area, the shop floors, you have humans and robots, they are working in shared space with almost no shared goals. Like humans' jobs are different, robots' jobs are different. Then there can be areas where we expect humans or robot to cooperate towards a common goal. And there can be space which is possibly shared, and it could be partially shared or completely shared, and there is some kind of cooperation. And then there can be, so cooperation can be, for example, for the surveillance, the robot is moving around in a colony. You expect that you show him your iCard when you are entering a colony, right? Campus. That can be cooperation. Then there can be collaboration where human and robot work simultaneously on same goal, same objective in a shared space. So these are the three things we are talking about collaboration. Right now, our aim is to talk about collaboration, right? So we are moving from coexistence to cooperation, coexistence to cooperation. We are talking about collaboration right now. Okay, so let us take a very simple scenario of domestic robots for domestic help, where the robot is expected to bring something from one place to another, say a fridge, open the fridge, and then place all the important material that is required to for today's cooking in the kitchen. So it has to pick an item from, there are so many objects, and but those objects you can see they can have similar appearance. Two bottles, one could be of a sauce bottle, that can be any other bottle of, say, pickles, and two bottles could be same. Now, how does it identify? So the question is, what object? When we talk about pick and place, what object? Where is the object? And where to place the gripper? Not only that the object identification is important, but how do I place the gripper so that I can very efficiently put the object, pick the object and place it somewhere. So all this requires vision-based scene understanding. So scene understanding is the crux of all that we work, those people who work in vision-based robotics. The crux is, how do we make robot understand the scene, right? Like, think of understanding by a human. The moment you show me a scene, I can immediately identify where is the tree, where is the house, where is what, and accordingly I can act. The same kind of intelligence is expected from the robot. The other thing is cooperation, where some puzzle is to be solved or some educational things are to be done, and it is with the help of a robot we are able to do. And in case of vision-based collaboration, serious applications, as I told, like surgery. Here you can see that one robot is also involved here in the surgery by looking at some, by applying some vision-based understanding of the object. So vision-based techniques, they basically, if you look at the simple application of, it's a simple Arduino board, using Arduino board project, where we are expecting the robot to follow or track an object based on its appearance. Okay, so vision-based, and just a minute. So in vision-based human-robot collaboration, what is important? First of all, detecting an object and locating where exactly is the object. And for it, it is a video processing. The robot is actually processing a video. So important is object tracking. How do we track the object? So the question is, what object? You should provide some information about object in the initial video frame. That is important. Somebody, Kamesh, is asking, is it like object following robot? Not always object following. There can be many tasks. For each task, which is a vision-based task, you need to have a understanding of the scene. When you say understanding of the scene, just a minute, please wait. If we talk about the understanding of the scene, so you have to identify the object of interest from the scene. And the object of interest can be, not always followed, but track the object in different cases. Today we are going to talk about more about object detection and object tracking, so that we understand what are the various methods which are applied in the field of vision-based robotics. Okay, so some information, initial information, has to be given. Some information has to be given in the initial video frame, like where exactly, what kind of object I'm looking for example, right? So when I say object information, there is some characteristic, there is some feature of the object that has to be supplied, okay? Now, object detection, the question is, what are the candidate objects in each frame? So you are telling some information, you are giving some information about the object, and in consecutive frames, the robot should be able to identify the candidate objects. And then association. These are different elements of vision-based techniques. We start with object initial, like object information. I should have some prior information about the object. Based on that prior object, I detect an object in a frame, and then I associate with this object. Like there can be, the question can be multiple object, it can be single object. So from this entire scene, which detection corresponds to which object? If I say that pick a red ball, I will tell the child, pick a white ball and pick a red ball. So I'm giving him or her some prior information that you are expected to pick a red ball and a white ball. So which object is a red ball and which object is a white ball is what a child understands and immediately picks up for you as a task. Same thing we expect from our robot also, that which detection, which object representation corresponds to which object. In the scene, there can be plenty of objects. One of them must be red ball and another must be white ball. Which is which one is which, right? So the red corresponds to which and white corresponds to which. Similarly, now there is something like filtering. So in consecutive frames, in first frame, the object may be at location X. In the second frame, the object may be at another location Y. How do we filter? How do we find out similarity between two in the object's characteristics between two consecutive frames is important. So object location and the size, everything is to be taken care of for filtering out that these are objects of the same category, and this is exactly the same object that a robot is tracking in different scenes. So detection means generally what we do that nowadays we use some kind of bounding box or salient points, which we call as key points also. And then using those bounding boxes. So here, this is when I say bounding box, it is basically a detection. So when I write here, when I've written here, which detection corresponds to which object, which detection corresponds to which object. So you can see these objects are there, right? And each detection is corresponding to different objects. So this is a detection which is corresponding to this object. There can be object 1 detection, object 2 detection, object tree detection. So we associate with each detection an object of a certain type. Here it is an object of this type, here it is an object of this type, and an oval object. And then in filtering, let's go to the next frame. In the next frame, maybe this object goes somewhere here. It comes somewhere here. But I'm interested only, suppose, in a single object. So I will be looking at its characteristics in a consecutive, in a sequence of frames. That is, how does it move from this place to this place? So for me, other objects are there, but they are not of importance. For me, this detection is important, right? So detection here is basically an approximation of the location, size, texture, shape of the object. So detection means we are looking for object representation so that we are able to locate an object of interest by understanding its features and estimating its location, like finding a bounding box. Association means given a noisy object detection. By noisy, I mean here you can see that you have only been given a very approximate position here, right? Object is not present here, object is not present here. So given a noisy object detection input in a sequence of frames, we associate it by recognizing the same physical object in each frame. So you associate same physical object in each frame. And then you filter. So we estimate the object location by motion estimation or similarity detection between object features in consecutive frames. So suppose in initial frame, it was somewhere here, right? By video frame, I mean that at each point of time of images taken, and these images are combined to make a video, right? So by frame, I mean the frame of reference that we are talking about, sorry, the frame that we are having at the moment, don't get confused by frame of reference. So it is the frame of reference in terms of the sensor that the robot is having. And in this frame, the object which was here goes to this place, right? So how do we estimate the similarity? How do we estimate how do we find out the similarity between these two objects so that I can identify that it is the same object which was present in the earlier frame, like here, and is now present here, okay? So, when we talk about these things, it appears to be a simple problem. But my dear friends, there are so many variations and so many challenges that make this object tracking problem a research problem. There are variations due to geometric changes. Like think of an object, human. Human can be walking, can be running, can be sitting, can be leaning. So because of the object changes, geometric changes in the pose, in the scale, if the same person is going from one place to another place, so if you have a static robot, he will only watch the object moving ahead, right? So what will happen? In his frame of, in his video frame, the object size will keep going down. Size, scale will go down. Similarly, articulation. There can be various geometric, like pose change and everything. There can be variations due to environmental changes, like it can be low illumination, it can be change in the background scene. In a cluttered environment, how do I identify the object? In any other environment with low illumination, how do I? It can be not only low illumination. Sometimes, you know, the car is moving from one place to another place, and the lights, surrounding lights can be yellow, can be blue, can be pink, and accordingly the appearance of the car changes. So how do I take care of all these problems? There can be occlusions also. So while the robot is tracking an object, there can be various occlusions that there can be partial occlusions or total occlusions at times. and so difficult to track the object. And then there can be complex nonlinear motion profile of an object, and that makes object detection and tracking even more difficult. Another important thing that is a challenge is there can be similar objects in the scene. All girls in the school uniform, all of them have haircut of similar type, or all of them are tying like they're having two ties, they've tied their hair. Then how do I identify that which object is girl A, which object is girl B, girl C, and girl D, right? So if there are similar objects in the scene, sometimes it becomes difficult. If it does not matter which object, then you can choose any one of the similar category. For example, if I ask you to bring a water bottle, so water bottle can be any of the 3 bottles that are there on my table. But if I ask you to go and talk to one of my students, and all 3 students are sitting, and you are approaching them from a door where they are not facing you, then which one is, say, Purnima, which one is Shubhangi, which one is another girl, is difficult for you to understand, right? So similar objects in the scene can also create problem. Another thing, think of various applications where we expect low memory footprint in drones or in robots. Then you would like to capture images of low resolution. When we have poor image quality because of internal or external factors, that also raises a lot of challenges in vision-based object tracking. Please feel free in asking questions if you have. So, object representations, so when I say object tracking, you should be able to detect the object. How can I detect the object? When I have a good representation of the object. Now, the main goal is to find out a representation in object representation that clearly distinguishes the object of interest from the background. So by background, I mean any object, anything that is not an object of interest will be called as a background. So the representation should be robust enough to deal with variations in scale, occlusion, change in appearance, or partial occlusion. There can be many challenges. The goal is to identify the object or detect the object amidst all these challenges. So in the literature, you will find in the research domains, you'll find object representations are in different forms, like they can be in bounding boxes, features within the bounding boxes, object features. There can be segmentation of the object, like it is segmented out from the image. There can be key points or salient points or position. So just to give you an idea, like here you have a position, right? One position. Here there are some salient points. Here it's a bounding boxes base. It's a bounding oval. Here there are certain, like it's showing not only single oval, but to be more precise, this is a crude approximation. This is a crude approximation. This is a more precise approximation of the location. Similarly, this is another approximation of the location. There can be contours. There can be many methods which can be used in object representation. But what is important within this box, what is the feature of any object here that can be easily understood by the robot, by the computer in the robot? So if we look at the early developments starting from, say, very simple developments like binary descriptors to distribution-based descriptors, differential descriptors, frequency-based descriptors. Various types of descriptors are available in the literature that help us identify objects, features, or characteristics. And so any object can be represented in terms of take any of the methods. These are different methods. Taking help of those methods, you can identify the object's features. And based on those features, what we will do, we will identify where are those in this entire image, what part of the image is having those features, what location, in what location of the image those features are present. So those, accordingly, the objects are recognized. Because we are talking about human-computer collaboration or interaction through vision-based techniques in 2022, where AI is in its peak. So we will be talking more on recent trends in object representation and the object detection using convolutional neural networks precisely. So convolutional neural networks are a kind of neural networks, and there are different types of methods that have been deployed and are very successful even in self-driving cars or in many assistive robotics. These methods involving convolutional neural networks are found to be quite useful. So there are methods which are known as two-stage methods. So what happens that initial feature extraction is done from the video frames, and then they classify, these methods classify that in this frame, there are objects present of category 1, category 2, category 3, like it can be bottle, it can be mobile, it can be a flower vase, it can be computer. These are objects present in of different category, and these locations will be given through maybe bounding boxes or through segmentation, right? Then there are single stage methods. These single stage methods are doing both classification and localization in a single pass of the image. So by single pass, I mean two-stage method, they require one pass through, say, convolutional neural network to extract the features, and then they require another pass through some classifier or through some regressor to identify where exactly is the location of the object. And in single stage method, both classification and regression, that means estimating the boundaries of the object, is a regression problem, right? So regression is done simultaneously. These are known as single stage methods. So why two-stage are required? Actually, initially, two-stage methods were developed, and they are still found to be quite, they have high precision as compared to single stage methods. So still there are so many researchers are working on single stage methods that can be as efficient as they can be as efficient as two-stage methods, and that these have to be as fast as any real-time requirement coming from different applications. Okay, so I told that we will be using convolutional neural networks. So I'll give here a very brief intro to what is a convolutional neural network. So convolutional neural network, my friends, is a kind of a neural network that uses convolution operation. Why? To extract features from the data, and later using those features, they build a prediction model. Prediction model means a model that can, a learned model, this AI model that is able to identify or predict the position of an object, or the presence of an object by looking at the object representation or object features. It is able to recognize that, okay, this object is present in this frame, and then where exactly is that present, right? So these are the type of neural networks. The convolution filters are learned here in convolutional neural network. The filters are learned through a machine learning process. So what are these filters? Filters are doing, basically they're filtering out. Their filters are used to recognize the patterns in different types of patterns. And using those patterns, objects are recognized. For example, in a face detection problem, features like eyes, nose are important. And each filter learns to detect a pattern. So let me take this simple example where the robot has to identify a person. So how he will identify? Through some method. And suppose that method involves presence of eye, ear, nose, something like that. So in a face detection case, this eye detector can be a filter which will learn to detect an eye in the given video sequence, right? So same pattern can be a different position in images, right? So for example, here there are 4 such patterns. So same pattern detector can move around. I request you to please pay attention. The same pattern detector can move around and detect eyes at different positions. So what is a convolution doing? It is moving around an image. It will move around an image and will try to detect patterns present in the image. Just a minute. So let us understand what is a convolution operation, my dear friends. So here is the image. Think of this as an image, right? I will be using a filter here. A filter is nothing but, say, an array, 2-dimensional array, 3x3, 5x5. It can be any array of any size, which is imposed on this, right? Which actually convolves with the, in the mathematical term, it says, we call it convolves with this part of the image. So convolution with an image block, right, outputs one real number, this one real number. When we slide this filter over the entire image to detect the same pattern, shifting block by block, we get an array of real numbers, right? So what happens that this is the output of the, so you get, so what you get, you for this part of the image, you get one output. When you slide it, put it here in this part. When you put it in this part, you get another value. When you put it here, you get another value, right? So all these values, outputs become, they also are in the matrix form, array form, and they become the output of the convolution operation, right? So suppose when we convolve this throughout the image, you see that this is the output that you get, right? Because I'm convolving it on the image, with the image. So for each filter, suppose you have a filter, let it be, say, 3x3 filter, you get an output array like this, right? So let me take an example. Suppose the image is this. Those who are having no idea of how the images are represented, let me tell you that if it is an RGB image, let's begin with a grayscale image. A grayscale image is represented by its pixel intensities, right? At each pixel, we find out the intensity, and that intensity is a number. The number is generally between 0 to 255, right? So these intensities are given. And if it is an RGB image, Then for each channel, red channel, green channel, blue channel, you will be having the value of the pixel intensity in green, red, and blue color. So you will, in that case, you will be having 3 channels. So suppose this is the value. So this is showing me the pixel intensity. Now, suppose this is my convolution filter. I will place this filter here. Now you can see that 1 is superimposed on 5, 0 is superimposed on 1, and -1 is superimposed on 7. Actually, I should not call it superimposed. Just I wanted to tell you that they're overlapping with these values. So what we do, we will be taking the dot product of this array with this array, right? So convert the image block and filter to a single column vector. Let's consider like this. Consider this as a this is the when we overlap it over this image block, right? On this image block, there are 9 values, right? I will put them in one vector form and put this filter also in one vector form. Now these two are vectors. Once you have put them in the vector form, you can take the dot product. So dot product will be 5 into 1, 1 into 0, 7 into -1. They're all summed up. So 5 into 1, 1 into 0, and then you can see that these are values, right? I compute them and the value turns out to be 2. Okay, I get one value by convolving this filter with the block of the image. Then what I do, I have the same filter. I now shift the position of the filter by, for example, a stride of 1 or by 1 pixel. I do the same operation. I will get another value, right? And then I do the same operation here and here. I will be getting 4 values this way. Then I will be sliding down here. I will find out the value here, here, and here, right? So what will be the output size after the convolution? Can somebody write down here on the chat box? What will be the output size? Please write on the chat box. You have got one value from here. When you take the dot product of the filter with this, you get one value. You get a second value here. You get a third value. And you get a fourth value. So in this row, you get fourth value. Now I put it down like here. Slide it down. Another value. Second value. Third value. And fourth value. So this way I have got, yeah, so somebody has written, it's a 4x4, Namrata, very right, you are. So it's a 4x4 output that I will be getting from this 6x6 input. 16 will be the dimension, I agree, but Kamesh, it will be a 4x4 output. It will not be a 16-dimensional output because it is an array form. So if I take RGB images, in case of an image with RGB channels, I perform convolution operation on each channel, right? So on each channel, I will be getting, say, for example, suppose the image was 6x6. I have applied a filter of 3x3 size. I got a 4x4 array, output array. That is a feature map that I'm getting. And for G channel, also I will be getting a 4x4. And for B channel also, I will be getting a 4x4. So you get 3 channels. I then take the sum of them. Make 3 copies of the filter and apply convolution operation. And then you will get 3 values, one for each channel, RGB. I add all 3 values of filter mapping to get a single output. So this W transpose R, W transpose G plus W transpose B. What is W transpose? If you remember, I wrote here. This was W. So I take W transpose, otherwise this will not be multiply, like how it's a kind of matrix multiplication that I'm showing, W transpose X. So similarly, W transpose R, G, and B. Then we take the sum of this. So you ultimately, finally, you get one output, even with a RGB channel. There are some kind of images which may have more than 3 channels. Like if a transparency factor, these days mobile phones are having wonderful cameras where they represent each image using, say, 4 channels, where a transparency factor is also there. There can be many channels. Like in satellite imaging, you can have 14 channels. In case of robotics, if there can be some sensors, different types of 6-7 sensors, and each sensor can give rise to 1 channel. And so there can be many channels. But in case of all the channels, when we apply convolution operation, we sum up the values coming from channels. So ultimately you get 1 feature map from 1 filter. So convolution layer, you have, like you can see, suppose there are, now, 1 filter will detect I, another filter will detect maybe trees, the 3rd filter may detect something else. So think of a pick and place kind of task, where the robot is expected to open the refrigerator and pick some objects. So maybe 1 filter will learn all milk bottles, another filter will learn all fruits of type A, fruits of type B, vegetables of type C, and so on and so forth. So you need to have many filters applied to an image, and that is what is known as a convolution layer. So a convolution layer consists of many filters. So input image of size n cross n, and suppose there are h number of filters, each of size f cross f, then the output will be a feature map. These are features extracted from the image, and each feature map will give rise to, there will be h feature maps because there are h filters. Each filter is trying to detect some different pattern, right? And each feature map applies its own bias, so the output becomes Z is equal to W transpose X plus B, where X is the input image, and say here you have a different number of filters. Now I come to activation map. So what is an activation map? My dear friends, what happens? These are all linear operations, these are all affine types of operations. These affine types of operation, W transpose X plus B. So if you have to model the non-linearity, how do you model the non-linearity? In order to represent non-linearity, model the representation of non-linearity, non-linear functions are applied on the outputs of the convolution layers. So these are nonlinear functions which are known as activation functions. So an activation function is applied on the entries, each entry of the feature map, to get the activation map. The output becomes something nonlinear values. So for example, if we have, suppose, 6 filters, right? You want to detect 6 different patterns. Each filter is of size 5 cross 5. We get 6 separate activation maps, right, from an image of size, say, 32 cross 32 cross 3. I get a downsize, as you saw, from 6 cross 6, we got 4 cross 4. So downsized channels, and there are 6 channels. That becomes output of one convolution layer. Output of one convolution layer. So I just wanted to show you some of the things that our students are doing, like plant disease detection problem. One of my students is doing. This is the input image. These are the feature maps, activation maps. So these feature maps are trying to detect, some are detecting, say, the boundaries, some are detecting the distinction between a disease, as trying to find out the heat maps, different, not heat maps, basically these are activation maps. In case of anomaly detection, wireless capsule endoscopy, where you have to apply an intelligent technique so that the robot is able to understand and do surgery properly. So here is a bleeding image in endoscopy image, and you can see that these are the activation maps that are shown. So my students Samir and Purnima have been working on this. So you will find that some of the, the question is how many filters to be applied. So it depends on the application and the data input type. And typically a sizable number of filters are chosen. So suppose your image is say 224 cross 224 cross 3 with the RGB image, you may apply initially some say 32 filters or 64 filters. So see here, you can see that 32 total filters are taken, and each filter is giving rise to some pattern. This is learning some pattern. Some of the patterns could be similar. There is redundancy, of course, in these filters learning, but this filter and this filter, they are learning almost same thing, right? This filter and this filter, they're learning almost the same thing. Still, the redundancy is kept because sometimes if some filter fails to learn a pattern, there is another filter which is able to learn the pattern. So the output dimension is something like, suppose the dimension of the input image is n cross n, and the filter is of size f cross f, then n minus f divided by the stride. Stride means when you are moving one, and if you are taking a gap of 1 pixel, that stride is of 1. If you're taking a stride of 2, then it is different. So like you're leaving 2 pixel and then you are doing it here, taking the convolution operation here, and then you are leaving 2 pixels. You are just dropping 2 pixels and you go to this. So then the stride is 2, and so on and so forth. So, right, so a typical CNN architecture participants looks like this. This is an image. Then there is a convolution layer which applies several convolution operations with several filters. Then there's something called pooling layer. I will tell you what is pooling layer. And this again convolution layer, pooling layer. There can be other layers as well. These days, you have attention layers, you have normalization layers which are present, but a typical CNN architecture consists of this. And these layers can repeat any number of times. Once, so what are these doing? What are these doing? They are learning the representation of the object, or they are learning the features or patterns in the image. And then once learning is over, they are flattened. It was like a 4 cross 4 filter, so they are flattened. It will become a 16 cross 1. And then after that, they are sent to a normal neural network, feed forward neural network to do, say, a classification problem or a regression problem. So how flattening is done? Suppose you have got 2 filter outputs, feature maps, right? So you will first put all the entries of first feature map and then second feature map. This is how you do it. And then you send it to fully connected map. What is a pooling layer? Well, when the images are large, one needs to compress the same, right? The idea is to make the representation smaller and to make the output volumes more manageable. There are 3 types of filters, pooling, which are generally used: max, average, and global average pooling. So what it does, it downsizes it's like undersampling of something. All right, so in that case, fewer parameters are needed to extract features for pattern recognition and characterizing the image. Max pooling, I seek your attention. What do? We take different blocks in the feature maps. So this is the feature map from filter 1, and this is the feature map from filter 2. So what I've done, you can see, I've taken the max of these 4 entries, 7. Here the max turns out to be 0. Here the max turns out to be 5, and here 4. So that is what we will be doing. We'll be skipping all those values. We will only be taking max values. This is known as max pooling, my dear friends. Similarly, average pooling will take the average of all these 4 values, like 3 plus 2, 5, and 7, 12, and then 1, 13, 13 by 4, which is approximately equal to 3. Similarly, other. And then global average pooling is recently being used very much in building the CNN models. So here we take the average of all the values, global average pooling, right? In the each channel wise, we are doing it. Well, there are, as I told, there are different methods, 2-stage methods and single-stage methods. So I first talk about this RCNN, which is still one of the most celebrated object detection method. I'm talking about object detection method, right? So what happens initially from here, region proposals are calculated, right? Propose category independent regions of interest. Category independent means whether it is a horse or a man or some background, we are not worried about the region, but we are worried about that there's some saliency in this part of the image. And that is why these regions of interest are calculated. Approximately per image, approximately 2,000 region proposals are calculated initially. And then after that, so we use, so what we use, extract regions. After extraction of regions, these warped regions of same size, they are passed through a convolutional neural network to understand the object representation, to learn the features of the object. And then each feature is passed through a support vector machine, which is a classifier, which is a binary classifier. And it checks whether this object is present, this object is present, this object is present, or so on and so forth. So each feature is sent to a binary classifier. So first of all, category independent region proposal, define the set of candidate regions for the detector. And then a large convolutional neural network is used to extract fixed length feature vectors from each region. And then a set of class-specific, say SVMs are chosen, support vector machines, class-specific, like it can be aeroplane or not, it is man or not, it is water bottle or not, right? So selective search is used here. So initially very tiny regions are created, and then based on the similarity of 2 regions, they are grown. So region growing is done through by checking the similarity of neighboring regions. And so you can see that the objects are detected accordingly in the images by region proposal growth. So as I told that images, region proposal, regions of interest, each region of interest is sent to the convolutional neural network, ConvNet, and then this is binary classification is done. Well, this method was very precise, very efficient. But what happened, that this was very slow because each region was passed and there were approximately 2,000 proposals for each image. So just so that nothing is missed out. But in this case, when nothing is to be missed out, a lot of processing is required. So faster RCNN does not use a special region proposal method. Rather, they use a region proposal network, which learns itself to propose a region, right? So it itself learns to propose a region. So this is also a convolutional neural network which learns. And then those learned regions are sent to a classifier along with a region of interest, the feature maps of those regions. Then the classifier finds out whether those regions are actually objects of interest or not. I hope I've made my points clear. Any questions here? Please feel free in asking questions if you have any. It seems there are no questions. Are you not finding it interesting or of interest? Please feel free in telling and giving your feedback. No issues. Are you able to understand? Please write yes if you are. Okay, Anil, thank you. Thank you all. Thank you. All right, so it's okay, fine. Thank you so very much. So, well, I'm giving you only a bird's eye view of these algorithms. When we maybe at some other point of time when you attend our programs, we will give you in details how do we apply them in for real life applications and real time scenario. All right. There is another very celebrated algorithm which is known as YOLO, you only look once. It was a sensational algorithm and it is considered to be one of the most important real-time object detector, and it is a single stage object detector. Unlike the previous one, faster RCN, which is a two-stage method, this is a single stage method, right? So because of the name and the kind of work it does, this is one of the most celebrated algorithm. So it trains the single CNN once only for all the objects in the scene. So for all the objects, it is one pass of the image and it is able to identify. The basic idea is predict a class and a bounding box for every location in the image. So what do? They make a grid of the image. Each cell in the grid, you can see here, if each cell in the grid identifies whether there is an object of interest or not. If there is, where exactly is that? So where exactly means it identifies a bounding box. So each grid here is processed by the convolutional neural network by looking at the feature of the object, and it identifies. So you can see here that it outputs a bounding box and a confidence score. So each cell will be confident that yes, there is an object, or will not be confident. So there is a probability score that is output along with the bounding box dimension, that is height, width, center, everything is given. And then there is a class probability map. So first is that it is confident that there is an object, and this is the bounding box of the object. The second is what category of object is this? Is it a table or a dog or a cycle, whatever it is. So it is computationally fast, can be used in real-time environment. It globally processes all the image only once with a single CNN, and it learns generalizable representation. That means if you train it in for some data, for example, although this is not very what should I say? By generalization, I mean that if it is able to generalize well for other data samples as well. Suppose you have shown data of Indian roads for a self-driving car, and you want to generalize it well for, say, Japanese roads or European roads. The car may not be able to drive either in India or in Japan because of the environmental changes, right? So generalization here means that in the new setup, new environment also, it is able to detect the objects correctly and maintains a high accuracy. So how does YOLO work? It only looks once at the image. It needs only one forward propagation through the network. It uses features from the entire image to predict each bounding box of the object. And it also predicts like all bounding boxes across all classes in an image simultaneously. Not like only dogs, not only like bicycles, and then table. It's not like that. All the different classes of objects that are present, it will identify. Those which are labeled to be identified, not always like for example, in the background, there can be trees, there can be road signs. If they're not to be identified as per the data set requirement, that will not be identified by the YOLO. It then outputs recognized objects together with the bounding boxes. The YOLO design enables end-to-end training and real-time speed while maintaining high average precision. And let's take a demonstration of a YOLO with another very important real-time a single shot detector, single shot multi-box detector. There's some question, it seems. Anil Sharma is asking, hello ma'am, is there any trade-off with reduced computational complexity with respect to accuracy of YOLO? Very good question, Anilji. So what happens that when we are trying to make it fast, there is likelihood that the precision will be low. So faster RCNN and YOLO. So initially when YOLO was introduced, faster RCNN was way ahead of YOLO in terms of precision. But in terms of fastness, in terms of timely prediction, YOLO was better. So 71% precision of faster RCNN with say around some 60s, I don't remember exactly, the precision was there of YOLO. But then now what is happening, people are improving. This I'm telling about 6-7 years ago. Things have changed drastically, in the field of single shot object detectors. So many new algorithms have come up. YOLO still stands at par with many such algorithms. It has many weaknesses, but over the years, different versions of YOLO have been introduced, and they are proving to be quite efficient. So let me take a moment to show you another screen. So here, I hope you can see. So these are YOLO versus SSD. Let's see, both of them are able to identify different, think of an application of self-driving car. Here is YOLO, here is SSD. So sometimes YOLO is able to do better, as you see here, and sometimes SSD is faster, right? So initially up to three versions of YOLO and SSD, both of them were competing with each other, showing that they are doing better than the others. But now SSD's philosophy of object detection was adapted by many other like M2DET, efficient DET. New detection algorithms have come up and they are doing much better in terms of object precision, as well as fastness. So with this, I go back to the slide that yeah. I stop it here. Because this will keep going. Let me stop. How do I stop? Yeah. So that was for object detection. Now, object detection, because the object detection means we are looking at one frame. In each frame, we are detecting the object. But now think about keeping track of this object. Robot is moving to pick up that object. So in each frame, the object will start looking bigger and bigger, maybe size, and position may change. Think of the robot moving in your house, going towards the fridge and taking out one milk bottle, right? So definitely the object will be changing, but the object itself can move. There can be many things. So association and filtering are two other aspects with objects, and there are methods which are single object tracking methods and multiple object tracking methods. And a lot of research is going on, and this research field is growing like anything. I would say that with the artificial intelligence that is there in place, new directions and dimensions have been added. So object tracking methods, if you look in the literature, there are two types of method. One is correlation filters. So those filters, they identify objects, and then those filters try to correlate in the next frame where will be the object. Now, so in the next frame, the object can be at a smaller scale, the object can be at a larger scale, object can be moved, might be moving. So all these things have to be taken care of. So correlation-based methods, which are classical methods, are still being used very well. And there are various types of correlation filters which have shown improved performance over the years. And convolutional feature-based correlation filters also exist. The other methods are deep learning-based methods, which I just told you one, like YOLO is an object detection method. Similarly, you have deep learning-based object tracking methods. So these deep learning methods generally used, say, autoencoders, or autoencoders can also be convolutional neural network-based autoencoders, or they can be Siamese network, that is twin networks. There are two networks which are parallelly working to check the similarity between the features of two different objects, right? So here is they say one image, the another image, which is a previous frame. In the previous frame, object is recognized, the next frame, and then in the next, say, consecutive frames, where is the object? Based on the similarity search, the objects are recognized. So various types of methods are available, and I will not go into details of those methods. I will request you to please, if you are interested, you please go through these important surveys of correlation filter-based object tracking techniques, multiple object tracking techniques, literature review, and recent advances in single object trade. These are beautiful reviews. And yes, so then the future, before I finish, I would like to say the main goal in human-robot collaboration is to understand and develop autonomous intelligence robots that help people live better. Help people live better in whatever way you think, whether it is secure and safe, safety of people, for defense and security robotics, rehabilitation robotics for medical and healthcare, surgical robotics, or it can be social robotics in schools, in public places, or domestic help robotics, right? So people, like, that we are a very young country, but there are countries like Japan and China, Japan especially, their average age is very high. So they do not have people who can talk with elders. So they need robots who can talk to them, right? Who can keep them engaged. So life better. So understanding humans' social and physical interactions, monitoring human behavior, and to understand and predict the types of help people need. All this can be done only when we apply the traditional knowledge and of robotics with artificial intelligence. We combine these two. Then only we can come out with beautiful solutions which are useful for the society and for research itself. So with the development of AI, human-robot collaboration field is growing rapidly, my dear friends. And if you are young and if you have interest in this area, I suggest you pick up this area, because this is still in its infancy. In spite of all the developments that have taken place, the field is still in its infancy. And there are a lot of people required to work in this area so that the growth, we can have sufficient growth of the subject. These are some important references that you can go through. And that is all from my side. I wish to have a little question answers. So I've kept a little time for question answers for you. Thank you, my dear participants. And I'm stopping the share. And I request all of you to please open your videos so that we can take a screenshot. That is a mandatory requirement for all GIAN courses, right? May I request all of you to please open your videos, and then you can ask questions. Amit, how are you doing? So Namrata ji, you are from where?
Ma'am, right now I am doing my PhD from SGS ITS Indore.
Okay, very nice.
But I am working in Jabalpur Engineering College, ma'am.
Oh, you are from Jabalpur Engineering College.
Yeah.
Very nice. Okay. And Manish Shukla is there. Kamesh ji, please open your video. Yes, yesterday he was facing a lot of problem, like what to do. GIAN portal, in fact, we have been writing to GIAN office a number of times. Unfortunately, people are facing problem. I hope yes, they will come out with some solution. Yes, and yeah, so many of you were facing problem, I know. Anil Sharma ji, yeah, you can all please put on. Hello. Amit, you are here. I'm so glad that you're here. Please put on your video. And who is connecting to audio now? Ramya, you can open your video, because this is required. In fact, we want people to. Madhuri, thank you. विजय आपको भी अपना वीडियो खोलना पड़ेगा. Vijay, you please open your video. And who is taking the screenshot? Vijay, you will be taking? Am I audible? Am I audible?
Yes, ma'am, you are audible, ma'am.
Okay. So because today, like, there's a lot of uncertainty with the network that we have. There's something wrong. All right. So Professor Meetha, Professor Amit Kumar, may I request you all? Vijay, आपका ही नहीं दिख रहा है, पता नहीं. हाँ, now yes. Okay, fine. Okay. So any questions if you have, you can definitely ask in between while we are taking your videos, screenshot. Vijay, you are taking the screenshot, right? Vijay, you are muted. Are you taking the screenshot?
Yes, madam, I've taken one.
Okay, fine.
Okay.
Fine. So any questions you have? No questions? So the professor, Domenico, is very much interested in accepting his students for his for internships because he has excellent lab and he wishes to work in collaboration with Indian students. So may I suggest you all, please be very attentive in his lectures. And if you try, if it's always good to ask questions, especially in online classes, you know, when we don't see participants' face, we are not aware whether the participant has understood, whether he's appreciating or not. So please keep asking questions so that keeps the online session alive. Right? With this, I thank you all. On behalf of the organizers, me and Vijay Gupta ji, we thank you all for being present here. We hope to meet you tomorrow, 2 p.m. Please join before 2 p.m. We will have a short inaugural session and then keynote session by Professor Domenico. Okay. So that's all from my side. Thank you. Thank you all. So I take your leave?
Ma'am, I have a question, ma'am.
Yes, please.
Ma'am, this the link which is being placed here, like that YouTube link, right, ma'am? Will it be in YouTube for some times? I mean,
yes.
Or after this ending session, will the video will be saved or be deleted, ma'am?
Yes, no. You will be provided the video links of YouTube. And what we will do, we will share a Google Drive with you. In that Google Drive, every day's lecture material will also be given. And there will be one text file in which video link will be given of every day, right? So you can use that video link.
Okay, ma'am. Thank you, ma'am.
Okay, thank you. So I take your leave. Have a nice evening. Relax, enjoy, and have a good tea or coffee with your friends and family. We'll be meeting tomorrow.